less than 6. By the way, the word essay is a synonym for large task or travail or burden, so essay, aptly named. Voltage difference, that's a fancy phrase for saying, what if you got more than one battery? The nice thing is, if I've done my job right, I'm hoping that we'll be able to intuitively just kind of figure out what to do. So here's the first question. Suppose I connected two 1.5 volt cells in series. What do you think the net voltage as recorded by the voltmeter would be? 3.
Okay, smart guy.
And that's an easy way to bump up voltage. Add another battery in series. This is why, for example, most flashlights are in series. You need a higher voltage than the battery is capable of putting out in order to get the bulb to light. Yes? Will we do any labs this year with making circuits? Probably not. Sorry, it's the Physics 12 tyranny. I will do, that's a bit of a fib, I will end the year, I hope, with one fun, cool lab right near the end. It's one of my favorites. Yeah, we're going to Playland. That's applied physics. So, explain your answer using principles of physics. If you want my ski hill analogy, you can say, hey, the mountain is 3 volts high, but we were too cheap to build a chairlift to go to the top. We built a chairlift that takes you halfway, and you built another chairlift that takes you halfway. Takes you all the way. In many portable appliances, CD players, flashlights, etc., 2 or 4, batteries are used in series in the diagram above. In series, this increases the total voltage. Now, there's a bit of a problem. True? If we increase the total voltage, what happens to the total current? Goes up, goes down, or stays the same? If this number gets bigger, what happens to that? This system, while increasing the voltage, will drain the batteries way faster because now you're pulling electrons at a faster rate from all of them. And that it's the same current coming out of each battery, so the same number of electrons coming out of each battery, so you're going to drain them faster. So the problem with doing this is now each cell has twice or 4 times as much current, which means they're only going to last half as long or a quarter as long. And this is why flashlights burn out so readily. They don't last very long. What do you think the effect would be of connecting cells in parallel? How many volts do you think are running through that resistor? Lena, you're right. Loud and proud when I say you're right, you can... Yeah. Because I can ski this run going downhill, that has to add to 1.5, or I can ski this run going downhill, that has to add to 1.5. But the nice thing about this setup is that each cell now is only having to supply half the skiers, half the current. Those batteries will last twice as long as just one single battery. And if you want the analogy, at the bottom of a mountain, there's 2 chairlifts. They both lead to the same location. Half you can go up that chairlift, half you go up that chairlift, but ironically, we have less current because V total is smaller. Okay? If we wanted to measure this, we would have to not connect a voltmeter, for example, there and there. That wouldn't tell us because those are the same height. We'd measure 0. You would probably connect a voltmeter right there. That would probably be the best place. You'd measure the drop across the resistor. That would tell you what you must be getting from the battery. Is that okay? Wow, many interruptions today. So rechargeable batteries are charged by connecting them to a cell that forces current back through the cell. So here is a rechargeable system. If we connect a 1.5 volt cell to a 6 volt charger, do you notice these batteries are pointing against each other? First of all, what do you think the direction of the current will be? Will it be pointing to the left or pointing to the right in that ammeter? Who's winning? Braden. Current is going to flow this way. What do you think the net voltage would be here? 4.5. So, Spencer, in our ski hill analogy, cells in series, for example, if this is 3 volts and this is 3 volts, that's the same as a 6-volt battery. It's like a 2 chairlift ride to the top of the mountain. 3 volts, get off, get on the next chairlift, 3 volts. And this is how we build batteries that are bigger and bigger. I think I said to you a while ago, if you took apart one of those rectangular 9-volt batteries, you'll find inside there 6 1.5-volt batteries. I think it's 6 AAA or 6 quad A inside there. And they're stripped of their fabric and shells and everything, but you'll see, oh yeah, there's 6 little cylinders wired in series. In our ski hill analogy, in the cells in parallel, that's like 2 chairlifts, both of which lead to the top of the mountain. Oh yeah, turn the page. Opposite cells are like one big, so the one that we just did, you would have a 6-volt chairlift going up, and then for some reason you'd have a 1.5-volt chairlift taking them down, and now what height are you at? 4.5 volts left. There's where my ski hill analogy breaks down. I don't know, are there chairlifts that take you down lower to other locations? Usually they'll just assume you're going to ski. So we've done pretty good with our ski hill analogy, though it's held up. So, by properly labeling the circuit, we can find the difference in voltage, the potential difference at various points in the circuit. Keep in mind, positive is higher, negative means lower. So if you're going from positive to negative, you're losing voltage. If you're going from negative to positive, you're gaining voltage. Current flows downhill. Plus to minus means a downhill loss. Minus to plus means an uphill gain. Comic for you to read. Hey, golf comic. We're going to scribble out B. For example, we're just going to do A. It says, find the voltage difference between points A and D. Okay. This actually isn't too bad a circuit. We can analyze this. First thing that I would do is I would label downhill. Got that? Then I would say, did they tell me total current? Because if they did, this question's going to fall apart. Did they tell me the total current going through the battery? They did. What is it? You're right. 0.7 amps. Right? Right? Yeah. So that means I have 0.7 amps right there, and I also have 0.7 amps right there. And I guess in mystery resistor R, I also have 0.7 amps. Because there's no forks, no junctions. Knock, knock. I know 2 things. In the 1 ohm resistor, in your head, how many volts do I lose in that 1 ohm resistor in your head, please? 0.7. How many volts do I lose in the 40 ohm resistor? I think 28, but double check me. Okay. Now, it wants me to find the voltage difference between point A and point D. I think that's going to be the voltage loss in mystery resistor R. Okay. I know 2 things. I found whatever I can. The next step was to ski. Sarah, how many volts am I starting with from the battery? And I lose 0.7 and I lose 28. On your calculator, can you go 45 minus 0.7 minus 28 and hit equals? What'd you get, Kev?
16.3.
Say it again, you're right.
16.3.
And if I go through here, this is the last resistor before I get back to 0. How many volts must I lose going through the mystery resistor R? Kevin?
16.
It has to be. Now, I don't think I would ask you this as a written question. I might even say, by the way, how big is mystery resistor R? Because if I know 2 things, I know 4 things. How can I figure out how big that resistor is? Sorry? An equation? Which one? And this is what I would say to you. Somewhere off on the page, if you jot that down, for most of you, that'll be enough to rewrite it. R is going to be what over what? Can you do that on your calculator? 16.3 divided by 0.7. I don't think it's going to work out evenly.
23.285.
So I'll go 23.3 ohms. Okay. Ange, could I have asked you for the power now in any resistor? Yeah, power equals V times I, or I squared R, or V squared over R. I don't remember what I was trying to get at with the graphing aspect, so we're going to skip that. And we already finished example 5. We just found the resistor on the previous page, so we can skip that. What I really want to talk about is example 6. This is much harder than I will ask you. Caleb, please. This is much harder than I will ask you on a test. In fact, I stole this from a university textbook, but believe it or not, we can totally handle this. I would feel comfy maybe with this as maybe a nasty multiple choice, but I'm not even sure what, well, maybe. So here is a cell. It wants us to find the voltage difference between X and Y. I think to do that, Kyle, we're just going to solve this. Why is this so tricky? How many batteries? And I think they are facing each other if I kind of follow downhill from each of them. Okay. Well, which cell is bigger? 6. That's downhill. So I'm going to start to label downhill from there. Definitely downhill that way. Yes, from the positive. And so where it says direction for current, I'll circle that. Downhill is that way. It seems to be suggesting that right here current is flowing this. So from there, I guess downhill has to be that way. We loop around the bottom like that. Okay. Step 2 was find total current. What I really said is I'm looking for amps anywhere. Did they give me amps anywhere? I'm just going to zoom in a bit. I think if I do that, I can still get this all on one screen. Where'd they give me amps? 0.5. Do I know how many amps went that way? Oh, I got the direction that way. Sorry, I could have done that. Yes?
Yes.
Do I know how many amps went this way? Is it 0.5? It is 0.5 amps there? Or why not? I don't know how many amps are coming in this way. Okay, so I'm going to look there. Oh, how many amps are going through this 3? Knock, knock. What else do I know there? More specific, what's the voltage? 0?
Voltage drop? No.
I times R, kid.
You can 1 point.
Is it 1.5? Yes?
I was like,
Okay. Next step is to try and ski. Well, I don't know if, first of all, if I started here and went this way, that creeps me out because I'm going backwards through the battery, so I'm going to avoid that. If I start here and go this way, do I know the voltage in the 3.5?
yeah.
I do?
Is it 6?
No, that's 6. Do I know the voltage in the 3.5? Captain Obvious, say no.
Oh.
Do I know the voltage there? No. So that's not a helpful ski run either. It is always going downhill. The only run I can think of to try skiing right now is that one. That is always downhill, is it not? Okay. So, how high? How high? No. How high? 4.
He said that.
He said 1.5. 4. Yes? So, Caleb, ready? How high?
4.
I don't know. How high? 1.5. So, what must I lose there to get back to 0 here? Got to be 2.5.
Neighbor.
Right? Is that okay, Lyndon? This loop here. 4 minus 2.5 minus 1.5, back to 0. Is that okay? Yeah. Now, why is that nice? Now, I'm going to ski that run. How high? Minus, I don't know, minus 2.5 gets me to 0. What must I be losing there? Got to be 3.5 volts. Knock, knock. How many amps? And whenever I can find amps, I smile because that's the one that I need to have this question fall apart. How many amps are going through the 3.5 ohm resistor? Exactly. 1 amp. So now, where it says I equals, let's write 1 amp next to I equals. What about this I equals? How many amps? Don't say 1. I got 0.5 coming in. I got 1 amp coming in. This is the way they flow out. Has to be 1.5 amps. Has to be. Oh, how many amps going through mystery resistor R? By the way, how big is mystery resistor R? Is it 1.6 repeating?
Yes.
So I'll go 1.67. Okay, I think we filled in every gap. Now, what the question asked was, find the difference in voltage between here and here. How big is it? What do you gain? 4? What do you lose? So?
That has to be 2.5.
It has to be 2.5 also because it's parallel to this hill, which is also 2.5 volts high. So this still ties in. It's a more complicated version, but the voltage drop between X and Y, and I'll even put the wings on there now so that we know it's voltage and not velocity, 2.5 volts. I was going to say we handled that pretty easily. Boy, we didn't. Some of you are doing some bad math in your head or something, or some of you need to really work on the homework. Let me emphasize again, that's harder than I'm going to ask you, but really quite doable. What's your homework? Number 1, number 2, number 3, 4 is good. Five is good. 5 is a good example of a using principles of physics right to explain question. So it's saying what happens to the voltage drop across the 5 when the switch is closed. Does it increase or decrease? I would just solve, probably. Although I notice number 6 looks like the same circuit as number 5, but with no numbers. Resistor, 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 resistor. The only difference is all of these resistors are identical. If you can figure out what happens just based on what you know about adding a resistor in parallel and R total and V total, great. Or, since all of the bulbs are identical, make up a nice resistance. 2 or 5 are usually pretty good ones. Take it from there. When it talks about brightness, Caleb, this is your moment to shine. This is your moment. Shine. Bright. Nothing. Okay. What do I mean when I talk about brightness? Which physics concept are we talking about? What?
What?
It's not current.
Power.
Power. The wattage of a bulb.
The what?
Okay? In other words, this question is saying which bulb, what happens to the power? Wow. You are slumping today, my friend.
Because he walked home.
7 is good.
Why do you do that?
8 is good.
No.
9 is good.
Exactly.
10 is good.
So far,
11 is good.
we've circled every single one.
Didn't I thought I skipped one.
No.
In some universe, somewhere I did. But I guess not in your universe. Sorry, quantum theory. Although there's lots of time.
I did get a lot.